So today I am going to talk about in situ monitoring of transport properties of graphene during plasma functionalization. So I am talking about two different functionalizations, one with hydrogen, one with fluorine. So then use that understanding to make some energy storage device. So I'll explain what in situ means. So this means we monitor the transport properties while it is being functionalized. So not like ex situ.
Сегодня я буду вашим переводчиком на такой категории. Это Гамини Суманасекера, многие его знают. Говорите, когда нужно перевести то, что он говорит. Перевод нужен?
When you go, you will understand.
Yeah. По пути понимаю.
So first, why do we do this functionalization? Whole idea is to engineer the band gap. I hope everybody is familiar with the band gap in semiconductors. So you have the valence band and the conduction band. So to have electronic applications, you need to have a semiconductor, right? So metals, so they don't have band gap, they have overlap band. So then you cannot change the properties. But if you have a semiconductor, usually you have valence and conduction band. So then you can make it as an electronic device. Unfortunately, graphene, that has very interesting properties, but they don't have band gap. So if you look at this point, so they almost touch each other. So that's, we call the Dirac cone. So that means it doesn't have a band gap, zero band gap. So that means graphene is not useful for electronic industry because there's no band gap. If you want to use as a semiconductor, you have to open up a band gap. So there are different ways of opening up a band gap. One is, this is what I was talking. Graphene as it is, there's no band gap, zero band gap. That's no good. But if always you put graphene on some substrate, right? So if you have on a silicon or any other substrate, because of the interaction between the graphene and the substrate, it will open up a small band gap. Or if you use more layers, so this is single layer, zero band gap. But if I have two graphene layers like this, so then you have this, you can see these two, you have a small band gap open. So then you can have like different stacking. So then you can have even more band gap coming in. That's second way of doing band gap. Or you can make very narrow graphene ribbons. So if they are extremely thin or even narrow, so you can have band gap. It's because of the size effect. So then this one can have two different geometries. Like we call this one, you can see this is like a armchair shape here. This is more like a zigzag shape, right? It's like you have chalk or something. Okay, yeah. So you can see in this case you have this kind of. So other case you have like this. So depending on that geometry, you have different band gaps. Next one is graphene oxide. If you take graphite and oxidize it, you can put it in very strong acid. Typically people use sulfuric, nitric acid. If you do that one, so you will get all these functional groups, but they are not ordered. So they are very random functionalization. So, but this becomes an insulator. So that's also not good, right? So it's a very big band gap. So, but you can reduce it to bring the band gap closer. No. large band gap. So this is huge, so maybe greater than maybe 5 electron volts. This is insulator. But I can reduce it, like treating with hydrazine or treating with hydrogen. So then I can bring this band gap smaller, or maybe like that. So that's called reduced graphene oxide. That's another way to open up a band gap. Last one is use combination of graphene and boron nitride. So graphene is all carbon. Everything you have carbon, carbon, carbon. This is what graphene is, right? So but you can have boron, nitrogen, boron, nitrogen, boron, nitrogen. So this kind of similar graphitic structure, but all boron. This is the insulator. Yeah.
How do you grow such?
Yeah,
such
same way. So you like yes, yeah. So we have to introduce. We use ammonia borane. So then say, on the copper, I'll explain to you how to do that. But graphene has zero band gap. Boron nitride has large band gap. If you bring this together, you can get very controllable band gap. Okay, so you want
Как я думаю, нужен перевод, да?
Можно я поясню немножко? Я был на стажировке в университете Луисвилля и хотел бы немного пояснить, то есть сейчас тема графена это, можно так сказать, горячая тема, актуальна, и профессор Гамини ей занимается. То есть основная идея в том, что в сегодняшней лекции он говорит о том, что графен это проводник, это очень хороший, но сейчас все пытаются сделать различные транзисторы, различные медицинское приложение для графена. И нужен полупроводник. Вот он как раз показывает, что для графена запрещенная зона, это вот band gap, она очень узкая.
Ее практически нет.
Да, и
есть несколько способов
Гамини пытается модифицировать как структуру графена с помощью плазмы, с помощью oxidation.
Сделать несколько слоев, как мы видим, когда уже нет два слоя графена электрина, у нас увеличивается этот band gap, это запрещенная зона. Мы можем также сделать очень узкие полоски нано-гипсом. Он как раз говорил, что есть две структуры. Это в форме кресел, амчел, когда они идут такой структуры, и когда они идут зигзагом. Но он еще говорил о том, что оксид графена, он является изолятором, то есть он абсолютно не проводит ток. Но мы можем удалить часть связи, если обрабатывать определенным образом, например, другой концентрации. И у нас тогда будет то, что мы хотим. Мы получим ту запрещенную зону, какая нам нужна. Ну и также он говорит о том, что можно использовать вставки из бора и азота, да, нитрит бора, вот такие же гексагональные структуры внутри графена. И тогда у нас получается, что у графена она очень узкая, а у нитрата бора она очень большая. И мы получаем что-то среднее, в зависимости от того, сколько у нас нитратов бора, вот этих структур в веществе.
Также это позволяет получать транзисторы гораздо меньших размеров и по цене и качеству это будет гораздо выше, чем сейчас они имеют для силикона.
Okay. So what we are trying to do is use different technique. Just use hydrogenation. That means you attach hydrogen atoms to the graphene, or fluorination. You attach fluorine atoms to the graphene. So what happens in this case, the graphene, they all have sp2 carbon, right? So because it's a planar structure. So if you look at all the hexagon, you have the sigma bonds here, then you have this pc orbital. So you have delocalized electrons here. So they make this pi bonds, right? So you have 3 pi bonds. So, but this pc orbital has this delocalized electron. So what we are trying to do is introduce atomic hydrogen. So this is molecular hydrogen, right? If I put a plasma, so this will make atomic hydrogen. So you have these 2, then you have 2 electrons. So this atomic hydrogen, so that means it's positively charged, right? So those atomic hydrogen, they can come and take this electron away, because this is 1 less electron here. So you have this free electron here, delocalized electron. This H plus comes and take this electron away. So then what will happen? So you will lose some electron. If I put more hydrogen, you lose more electrons. So also in that process, it is going to make this. So this is how hydrogen is going to be attached to the graphene layer. So when that happens, this is completely sp2, you make sp3 structure, right? Because initially it is just plain sp2 wall. So if you put hydrogen combines like that, then it becomes sp3. So it goes from sp2 to sp3. So in the process, it's initially like metal becoming less metallic. So if you do it forever, what will happen? It should become completely insulated, because you remove all the electrons. So that's what we are going to study. So in the process, you can gradually increase your band gap, because initially you don't have any band gap. So by putting some hydrogen, you can make like that. So then put in more hydrogen. This way you can control the band gap. Same thing you can do with fluorine. Same thing, you can have fluorine gas. Actually we use carbon tetrafluoride. If I put the plasma, I can make F plus. So again, this F plus comes and attached to the graphene. Then again it goes from sp2 to sp3. In the process, it will go from metal to insulator. This is a very interesting physics problem, right? It's a phase transition from metal to insulator. So there have been interesting studies initially by Mott, Sir Neville Mott. He studied metal insulator transition. Later on, Anderson. So he actually got his Nobel Prize on this Anderson localization. So these are very interesting physics problem, metal insulator transition. So we are trying to study that transition here. Yeah.
Так, чем они занимаются? Они используют плазме, водороды или фосфоры. Они помещают наши графеновые слои. Так как у нас водород и фосфор заряжены положительно, потому что они ионы,
Это фтор.
они заряжены положительно. Соответственно, когда они подходят к углероду, к молекулам углерода, они свободные электроны смещают, они связываются с их помощью, и таким образом у нас остается меньше подходящих электронов. И наша запрещающая зона увеличивается. Таким образом мы можем эту запрещенную зону регулировать от того, какая у нас плотность водорода или фтора присоединенных молекул к графену.
Yeah, this interesting thing is like when you oxidize, they are very random. Like if you put it in acid, oxygen will be attacked very randomly, but this way we can do very ordered way. So very orderly we can do the functionalization with hydrogen or chlorine. Okay, so how we first, let me quickly, I think last time also I talked about how we make the graphene. I'll quickly go through this one. Actually, Alexi did a lot of graphene growth in the summer. So what we have is a simple reactor here. So we just pump on that one, it's under vacuum. So then we put a copper foil here. So then we first heat the furnace to 1000 Celsius with flowing argon and hydrogen. So that means not to oxidize the copper. Right? If you heat under air, you will oxidize. So that's why we use reducing agent. So we just heat the furnace from room temperature to 1000 Celsius while hydrogen is flowing. So we don't use just hydrogen because hydrogen is too flammable. So we don't want to have any accident. So that's why we use only 40% hydrogen in argon. So that's safer. So then after it reaches 1000 C, we introduce methane gas. Methane is the carbon source because I am going to make graphene, right? Graphene is all carbon. So what my carbon source is methane. So then we do it for about 30 minutes. So during that process, it grows graphene. So after that, we stop methane flow and just let it cool down still with hydrogen argon. I don't want to just cut down hydrogen, then again it can oxidize this. So we always make sure we have hydrogen flowing. So then at the end, we take it out. So we have graphene on the copper substrate. So if I want to use the boron nitride, instead of methane, we use ammonia borate. It's actually powder. So we just keep it here and heat it and let it go. So that way we can make similar way boron nitride.
Итак, как мы получаем наш графеновый слой на расцелении? То есть у нас есть печка. Здесь у нас идет откачка воздуха, то есть у нас здесь находится вакуум. Затем мы нагреваем ее до 1000 градусов, причем мы нагреваем смесь аргона и водорода, причем водорода на 40%, аргона 60%, потому что водород взрывоопасен, мы не хотим взрыва воды. Нагреваем до 1000 градусов, с ним выдерживаем и добавляем металл. Так как нам нужен углерод для того, чтобы сделать графеновый слой, он начинает осаждаться на нашей глине. И после 18 минут мы закрываем клапан, перестаем поступать метан, и печка охлаждается сама до комнатной температуры. Если мы хотим, чтобы это было нитрат хлора, мы добавляем сюда, насколько я понял, аммоний. Говорит аммоний. Химики есть? Нитрит бора.
Ammonia borate. It's a powder.
Да. Он у нас в качестве пыли, мы его нагреваем здесь вот, а потом, когда он нагреет уже 1000 градусов, мы просто открываем, и он осаждается.
I have a question.
Yeah.
Do you have a diffusion of ammonia borate inside the copper?
Yeah, it's the same thing. Yeah. What happens is it's a vapor, right? So boron and nitrogen vapor comes, so then it diffuses on the copper because there's no miscibility. So it's only just spreads on the copper. Same thing happens with the carbon. So carbon. No, so that's the thing. Carbon and copper, or boron nitride and copper, they don't mix. So it's only
Even on the high
temperature. Yes, yeah. But if you use iron or nickel, so that's why you grow carbon nanotubes. Yeah, because they mix in. Yeah. So with copper, there's no miscibility. Yeah. It's only just spreading over.
Вопрос, почему азот углерод и бор не проникают в наш образец из меди. Ну, Гамини говорит, что при таких температурах такого не происходит. Это происходит, например, с железом, но с нашим медью этого не происходит.
Okay, so this is the real experimental setup, like I said. So this is the reactor. So we have the pressure, so the pumps, so the flow controllers. So then usually we have the copper inside the reactor. So this is how it looks like. So all the components like pressure control and the flow control. These are just the details of the system. So what happens is, so when you take the copper out, so this is your copper piece, so you have graphene on copper, but we cannot use it because the graphene is on the copper, right? Now we have to remove that graphene from the copper. So how do we do that? We just, so this is your copper, we have the graphene on that one. So then what we do is, we first deposit some polymer. This is a PMMA, polymethyl acrylate. So we put spin coat this polymer on this graphene. Then we put it in the ferric nitrate solution. So ferric nitrate will dissolve copper. So then what happens? So this copper will be dissolved. What you have is this graphene with the polymer. So this is gone, right? So then only thing you have is the polymers, because you had copper. So then I had this my graphene. So now I put my polymer. So now when I etch, the copper is gone. So now I want to collect that piece. We can see because of the polymer, you can see the sample. Then I put my substrate and just take it out like that. So then what I do is we just put it in acetone and remove the polymer. So then you have nice graphene layer on the substrate. So that's what this is. So graphene on copper, then we put the polymer, then we remove the copper. So then take my substrate and take graphene with the polymer. So then in acetone we just remove the polymer. Here now we have nicely graphene on whatever substrate you want. So you can see how we do that. Copper, put it after polymer, we put it in ferric nitrate. So this copper is gone. So then I put here, I collect it on a glass substrate. So this is still polymer is there. When I put it in acetone, polymer is gone. You can see nice graphene on the substrate. Or I can put it on silicon substrate. That you can see very clearly on silicon. So either way you can fetch it to the substrate you want. You can make very large graphene this way. That's the nice thing in this technique. So whatever. So this is very large, this glass substrate. You can make any size you want. That's okay. Okay. So now once we have our graphene, so I want to do the plasma functionalization. How do we do that? So I have this plasma reactor. This is very simple. So another glass, the reactor here, quartz. I have this capacitively coupled plasma reactor here. So this is actually a simple capacitor, but it is connected to a radio frequency power supply. This is something like few hundred megahertz. So with somewhat few hundred watt power. So then you just introduce, also it is, you pump on the system, then introduce hydrogen gas, so then ignite the plasma. So when you apply the RF power, you can see very nice color of hydrogen plasma. It's a pink color. So then I have my graphene sample, I mount it onto this some sample holder. So that is actually in a long sample probe here. So that goes inside the plasma reactor here. So my sample, graphene sample is, this is where the sample is. So one thing you have to make sure is, you don't want sample to be inside the plasma. If you put your sample inside the plasma, you will damage your sample. Because plasmas are very fast radicals, right? Ions and atoms. So we have to make sure they are not inside the plasma fluid, because this is the plasma region. You just keep your sample somewhere here. So then I can study what happens when I start the plasma. So this is how the sample, so you can see that there's a heater, then I have all the wires connected to the sample. So all outside wires are coming here.
Ну, перевод этой части нужен?
Да, надо. Нам.
It's okay?
Да.
No, okay.
Так, как мы отрабатываем плазму наши образцы уже графена? Вот здесь вот у нас находится образец, здесь у нас находится серия катализаторов, часть заземленной пластины, а остальные у нас к генератору высокочастотных токов, то есть до мегагерц. Здесь у нас идет углерод. Здесь у нас находится плазма, по времени картинки она имеет розоватый оттенок. Важно, чтобы у нас наш образец не был в плазме, иначе с ним прямые последствия. И какие измерения мы делаем с ним? То есть вот у нас есть термопара, мы измеряем разницу в температурах наших графеновых образцов. Так. Здесь у нас вот, собственно, как наш образец выглядит. Вот эта схема. Здесь это все у нас графен. На такой подложке у нас находится образец.
So basically we measure these properties, like we measure the resistance of the sample. So everybody know the Ohm's law, right? The resistance is V over I. So if I take the sample and if I pass a current and measure the voltage, from there I can measure the resistance. So since this is not a very regular sample, we use what is called the Van der Pol technique. This is a standard way of getting the resistance. So then in order to measure the thermal power, we just apply some heat pulse and measure the voltage across the thermocouples. So then also we can measure the difference between these two voltages. That will give you a temperature difference between the two ends. From there I can calculate the this thermoelectric power. So that's little detail, so you don't need. So just make sure we measure the resistance and the thermal power.
Мы измеряем сопротивление и разность температур, но мы говорим, что это детали, которые не стоит просто, чтобы знать, что мы измеряем сопротивление и разность в напряжениях на термопарах.
So this is how the sample is. So we have the two thermocouples. So then, because we need 4 wires to measure the resistance, right? So this is the. So I'll later explain the thermal power probably here. So, okay, let me see what happens here. So this is initially my sample resistance is about 1000 ohms. So then what I do is I plasma for about few seconds. So then I turn it off. So then when I look at the resistance, you can see resistance is increasing and it saturates here. So it goes to almost like 2000 again. So then again after sometimes I again turn it on for like few seconds, then turn it off. So then we can see again it goes here. So I can stop any way I want. Right? So I wanted to, initially it is like 1000 ohms, then I wanted to get to like 10,000 ohms, somewhere here. So that's initially, say, this is my resistance, so this value here. So then after hydrogenation, I can get to this point, that is this Y point. So then after every treatment, I measure the temperature dependence, because I can use my closed cycle refrigerator that can cool the sample down to almost 6 Kelvin. So I just do temperature dependence. So then I come here, do the temperature dependence. So then again I do and come here and do the temperature dependence. But every time what I do is I make it more insulated, right? Because I remove electron. So this way you can go, this is like 1000, here I can get to almost 10 to the power 7. That means I am going to more and more insulating. So in this process I am going to open up the band gap. So that's very controllable way of opening up a band gap. So this is for each functionalization, I just look at the temperature dependence. Good. Is that clear?
Нет, компьютер работает, это у нас проект. Так, ну, что мы делали? Да, проект. Что мы делали с нашим графеновым слоем? Мы включали плазму на буквально 5 секунд. После этого мы видели, что сопротивление выросло там, буквально с 1000 Ом до 2000. Затем мы снова включали на 5 секунд, и снова у нас вырастало от сопротивления. И так мы делали несколько раз, и мы получали за несколько серий до 10-кратное возрастание сопротивления. Что мы делаем дальше? У Гамини есть установка, которая может охлаждать образец до 6 Кельвин. Мы исследовали зависимость сопротивления от температуры. И делали целую серию экспериментов. То есть, чтобы, конечно, график. Вообще на графике?
А ты нарисуй.
Можно, конечно. Это у нас был график необработанного плазмы и графена. Что дальше? Сейчас эксперт. Температура. Здесь у нас наша сильная резистенция. Далее, после обработки у нас после первой обработки у нас выросло сопротивление, после второй и так далее. И вот, отлично. После этого мы, как видно из графика, получили фактически непроводящий слой. То есть его, здесь у нас еще идет не сопротивление, а проводимость. Проводимость входит практически мы из проводящего слоя получили изолятор.
Yeah, so you understand these curves, right? So this is more and more functionalization. So that means actually this corresponds to how much hydrogen is there, right? So, but we know, so this transport is governed by this equation, that is R goes like temperature to the power 1/3. This is called the variable range hopping. The mechanism is electrons hopping from grain to grain. So they always follow this relationship. So, but interesting thing is, if I plot resistance or conductance as T 1/3, like this, it seems to be okay.
maybe it will for some heating.
Yeah.
It will be reserved.
Right. So if I plot this, actually here I am plotting 1 over, that is conductance. So I can find one, this marked by red. So that one shows linear behavior reaching 0. So that means this is the critical hydrogenation for this functionalization. So all the curves below the red one, so you can see they are this one, right? So they have finite conductance at low temperature. But this black one, it becomes 0 before T equals 0. That means this is the insulator. So the definition for insulator is your conductance becomes 0 at some finite temperature. So metal means you have finite resistance at even lowest temperature. So since this is reaching linearly to 0, so we can identify this is very close to the critical hydrogenation. We call N is the hydrogenation, degree of hydrogenation. We call NC, that's the critical. So these are all metallic because they are finite. So this is insulated. So we can identify both insulating and metallic region. So now actually we can do some kind of scaling approach here. So now if I take each curve, like all these conductance curves, if I divide by this critical one, this is the critical one, right? Red one is the critical curve. If I divide every curve by this critical one, so actually it's very interesting. They all converge into one simple curve. So here what I did was every temperature dependence I divide by the red curve, that's the critical one. So that is actually this one, okay? It's 1. So the other one, they fall into different curve. So this is the nature of a phase transition. If we have a phase transition, it should follow some kind of scaling behavior. So you can see all the metallic curves, they all fall into this one universal curve. So this curve, unfortunately, we have only one insulating, so we couldn't get. Ideally, I would like to see more after this one, right? So they all should fall into this insulating curve. So this is the first time nobody has shown scaling behavior for metal insulate transition. So this is very exciting. Yes. Yeah.
What is the nature of these lengths, of these scales?
Oh, actually, the length scale is what is called the localization length.
What does it mean?
So that means how. So if you have very strong localization, that means your localization length is very small. If it is less localized, that means you have longer localization length.
But you are talking about the localization of electrons.
Electrons, exactly. Yeah, it's all electron localization. Yes, yeah. So this you can see the localization length becomes almost 0 when you go to the insulator. For metallic, it's very long, like almost 400 nanometers. Yeah.
Так, ну, мы берем самое интересное в этом графике, то, что мы еще не видели, это то, что мы взяли наш красный, в российском языке, кривая, когда мы отложим температуру в степени 1/3 относительно проводимости, она у нас, проводимость, идет к нулю по температуре. Выше наша графика располагается металлические свойства, такие как синий, зеленый и так далее. А вот черный, его проводили достигает нуля еще до нуля по температуре. Значит, мы достигли, что получили из проводящего изолятор. Так как красный является у нас критической прямой, то мы проведем очень интересное исследование. Мы определим значение других кривых на значение красного. Вот она у нас будет сама она определить все будет единица. Вот у нас те, кто показывают проводящие свойства, металлические. Они все идут к одной кривой в течение нашего значения. А вот наш изолятор, он идет по другой кривой. И Гамини сказал, что если бы мы продолжили эксперимент, то есть получили еще большее сопротивление, то они должны идти по этой же кривой, как проверяющие металлические свойства. А здесь у нас находится плотность электронов, и как мы видим, сначала у нас металлические свойства у нас была достаточно большая плотность электронов, и потом она начала уменьшаться, и когда мы пришли практически к изолятору, то есть у нас электронов стало крайне мало. И
Strong local.
strong. Yes. Это у нас сопротивление, то есть сопротивление у нас при этом вырастает.
I think I will just skip this one. I don't want to. It's too much detail. Okay, so then we look at the structural changes. So here everything we did goes transport. Right? So then each sample. So, but one thing we have to remind is, so when we do this plasma functionalization, so we have our sample here, right? So then we put few more control samples around the same place. So that means they all going to be functionalized similar manner. So that we use to do the Raman spectroscopy and XPS, X-ray photoelectron spectroscopy, because we cannot use that same sample. So, but we put some dummy samples so that we can use for Raman and XPS data. So let's look at what happens to the Raman spectrum. So this is the sample before hydrogen functionalization. You have, we call this is a G band. So G band means this is a vibrational mode, right? How carbon atoms are vibrating this way. So that comes around 1600 centimeter inverse. Then this is called the disorder band. So that means if you have a perfect graphene, you should not have any this band. So then we have the second order of this one. This is around 1300. So this comes around 2600. So this is the second order of this peak. This is always present. This is actually two four-node process. So you can see this is the signature of good graphene. You have D band, G band, that's this vibration. We call this is the 2D band. Okay, so you have very nice picture here. Now, after first functionalization, that means like after going from here to here, right? So after that one, what we have here? You can see now this D band becomes little stronger, right? So this one becomes weaker, and also this, you can see this new small peak coming here. Then also this also going down. So then when you go to next one, you can see this D band becomes even stronger, and this peak becomes more prominent, and this is becoming less prominent. So as you go on, you can see when you come here, this peak becomes much stronger, and this additional peak becomes stronger. So eventually, this becomes really strong, and this becomes really weak, and you have very distinct two peaks. We call, this is the G band, and this is called the D prime band. So there's an extra band coming here. And this 2D band is pretty much disappeared, right? So this is a very strong evidence for making even the sp3 structure, because this is corresponding to the sp3 Raman band. So this is very obvious. So we actually analyze this band. We just plot separately. This band I plot it here, and this band I plot it here, and you can see how they. Yeah.
We have a question.
Yeah.
Last plot, it's already not graphene.
Bad graphene.
It's not the graphene.
Which one? The
Last
seventh
plot.
The seventh one,
Oh.
the highest.
Seven, yes.
The highest.
oh, still I think you have some graphene, yes. Yeah. So, but that's why it is mostly everything is functionalized with hydrogen. So it's all become like all the carbon atoms, they are bonded with hydrogen now. So that's why it doesn't have the sp2 signature anymore.
But we haven't 2D band. We haven't 2D band.
Yeah, so that when you don't have any two-dimensional sp2 signature, this band also goes down. Yeah. So this is, you need to have sp2 structure to have this 2D band. So there may be some destruction also, but typically when you have all sp3, this band, the diamond doesn't have this band. There's no more sp2. Yeah, there may be some damage also. That's why it's almost insulated.
Итак, обратимся к хромовской спектрографии. То, что мы получили, анализировали наши образцы, то есть те, которые абсолютно чистые, после первой степени обработки, второй, третий и так далее. А у нас есть несколько пиков. Это у нас как раз наш G-band, это освещенная зона. Здесь этот пик у нас отвечает за sp3 состояние, то есть присоединенные какие-то нейроны, водород. Видите, когда при дальнейшей обработке у нас соединяется больше атомов водорода, и атомы углерода переходят в следующее здесь состояние sp3. Когда у нас нет этого пика практически, значит у нас хороший графен. Этот пик отвечает за наличие sp2 состояния. Как мы видим, при дальнейших степенях обработки у нас sp2 практически исчезает, а вот sp3 преобладает. Вот мы вывели на отдельной графике G-band и D-band, то есть за sp3 состояние, за запрещенную зону. Как мы видим, запрещенная зона увеличивается, а пик, отвечает за sp3, тоже увеличивается.
Okay, so same thing we did with the X-ray photoemission spectroscopy, XPS. So if you look at before functionalization, this peak corresponds to the sp2, and yeah, very small, it's almost zero for the sp3. But after functionalization, this becomes strong and this becomes weaker. So when you plot in stack, you don't see very big change, but if you plot this ratio, so sp3 peak becomes strong and stronger ratio. This is also another evidence for sp2 to sp3 transition. Yeah.
D-band is sp3.
sp3, yes, yeah. So if you take the diamond has very strong this band. There's no G or 2D band. It's only strong D band. sp3 is all D band.
То же самое мы получили для рентгена анализа, вот у нас был sp3 ниже, то, что было до обработки, sp3 совсем маленький, пик sp2 большой. Но после обработки у нас sp3 вырос. Вроде бы незначительное понижение пика sp2, но если мы сделаем график пропорций, то мы ясно видим, что идет возрастание пропорции sp2 и видно sp3.
Okay, so I'll just quickly go to the fluorination now. So we get the similar results. So now in this case we the fluorination. So again you can see the resistance around 1000 here. So then when we fluorinate, you can see it's again increasing. So then at the same time I can do the similar metal insulate transitions. So it's a very similar behavior. But in this one, I don't know to go through this one. So you can see again very similar Raman and XPS. But we already measured the band gaps after each fluorination. So you can see by using this simple Arrhenius kind of a conductivity dependence, this is the band gap. So you can get, if you plot log sigma versus 1 over T, you can get the band gap information. So if you do that one, you can see your band gap is gradually increasing. We can get to close to maybe more than 100, like 0.1 electron volts. We can open up band gap. So eventually it becomes almost insulated.
Ну, вот на предыдущих графиках мы видели такое же поведение при обработке фтора в плазме. То есть то же самое, у нас увеличивается запрещенная зона, увеличивается количество SP3 состояний, уменьшается количество SP2 состояний. С помощью следующей формулы мы получаем нашу запрещенную зону, то есть размеры в электрон-вольт, как мы можем видеть.
Okay. So now I'm going to switch gear a little bit. So we are going to talk about some application of this fluorination. So yesterday I talked a little bit about primary batteries. So most of the primary batteries, they are based on these CFX batteries, carbon fluorinated carbon. So these are the state-of-the-art primary batteries used in mostly your pacemakers and also for military people. So military people, they don't need rechargeable batteries. What they need is very high capacity primary batteries that can last 2 days. So these people go to the battlefield, they are mostly like 48-hour mission. So they don't want recharging. So, but your battery should be good enough for 2 days. So that means you should have good primary battery with long enough life cycle. So at the moment, best primary batteries are CFX batteries, fluorinated carbon. So because we now know how to fluorinate very controllable way, so I use that same idea and same parameters to make this fluorinated carbon.
Ну, коротко, в данный момент наиболее распространенные одноразовые батарейки, о которых шла речь, это фторуглероды, то есть они используются в военных целях, когда нужен достаточно большой запас энергии на вечное время, на 2-3 дня, насколько говорит. И сердечные кардиостимуляторы, которые вы не можете достать и зарядить, а он с вами на протяжении всей жизни идет. Вот. И это применение наших новых батарей, возможно применение, где мы применим эту технологию.
So what in this one we use same fluorination system. So you can see now fluorine plasma is blue, so hydrogen plasma was pink, right? So but in this one, similar reactor, but we have to heat the sample to make the fluorination process much faster. But we use, instead of graphene, we use multi-wall carbon nanotubes. So we start with multi-wall carbon nanotubes are black, right? So after fluorination, it becomes almost white. So that's Teflon, right? So Teflon is PVDF. So the fluorinated carbon, right? So we just start with multi-ore nanotubes, then I can fluorinate in a controllable way. So, but these are powders, so that's why, so we have to make sure this powder is kind of agitated. Otherwise, you only functionalize the surface of your sample. That's not good, right? So if I put my powder here, so if you put the plasma, you only fluorinate the top. So what we do is we attach some kind of vibrator here. So that will kind of shake the sample. So that way I can homogeneously fluorinate the sample. So this similar setup, so use this carbon tetrafluoride and ignite the plasma. So in this case I don't have to worry about damaging because these are large quantity of powder. Only thing is I have to treat it for longer time. So if I treat it for 8 hours, it's something like that. If I treat it for 12 hours, it becomes almost white. So that means I can change my X. So this CFX, I can go X from 0 to almost 1. So for different fluorination. Is it?
Перевод нужен? Установка почти такая же, как при обработке плазмы водорода, только у нас здесь больше температура, и вместо графена мы туда помещаем графеновые нанотрубки. Как мы видим в экстравирочках, они изначально практически черные, если мы их оставим там на 8-12 часов, они станут практически белыми. Мы достигаем количества фтора на углерод от 0 до практически 1 фтора к каждому углероду.
Okay, so what we get here, so this shows another picture of what we have here. So this is the sample, this is completely immersed in the plasma. So this is how the nanotubes look like. RF cover, CF4 gas coming, so vibrator, so everything is here. So now, so if you look at the XPS, so this is initially before we fluorinate, I have only carbon signature, right? So this carbon nanotube is only carbon. When I fluorinate for like 2 hours, I can see fluorine peak is coming here. So now if I fluorinate, also the carbon peak is getting weaker. So now if I fluorinate for 4 hours, you can see this fluorine peak is getting stronger, stronger, stronger. That means you are putting more and more fluorine into your CFX. So then at the same time your carbon signature is becoming low because this is a ratio we are looking at. So also if you look at the details of this C1SP, you can see this is the SP2 signature. So this SP2 becomes weaker and SP3 becomes stronger. You can see it clearly SP3 becoming strong and SP2 you can.
It's just we feel it again. Yeah.
Oh, wait.
I think we can wait.
Yeah.
Yeah. For a while. Yes, we'll come back.
Yeah. Last time I just put it will be 10.
Так, вот эти слайды можно придется.
It's not very good.
Как мы видим, после спектрографии,
This is nanotubes.
yes, nanotubes. После обработки, вот это график абсолютно необработанного вещества, абсолютно необработанных нанотрубок. Пик, отвечающий за СП2 под уровнем, у нас достаточно большой. А вот пик, отвечающий за фтор, у нас отсутствует. Когда мы обрабатываем в течение некоторого времени, то есть до 12 часов, пик, отвечающий за углерод, за SP2. Is this for SP2?
Yeah.
Is this SP5?
It's carbon, one SP, yeah.
Да. То есть этот пик, отвечающий за углероды, становится как минимум гораздо лучше, а вот количество углерода у нас подходит к фтору. У нас увеличивается со временем обработки, то есть наш интервал. Аналогичная ситуация с графиком по SP2 и SP3 под уровнем, то есть у нас идет SP2 до обработки, он преобладающий SP3 практически нет, но с обработкой у нас пик, отвечающий за SP3, вырастает, а пик, отвечающий за SP2, уменьшается. То есть вот у нас 2 часа, чистые 2 часа, 4, 8, 12 часов обработки.
Okay, so then if you look at the X-ray diffraction, so this is before fluorination, we have very strong this 002 peak. So when you fluorinate, that peak becomes weak and eventually becomes extremely weak after even 8-hour fluorination, because you make that nanotube, the lattice distorted. So this is because when you put more and more fluorine, your order is going to be destroyed. So that comes in X-ray diffraction, XRD. That's evidence of real fluorination.
Если посмотреть инфекционную картину, то если чистые нанотрубки у нас был пик, то с увеличением количества фтора у нас порядок в нанотрубках становится все хуже, что он практически исчезает. И мы видим, что после 8 часов у нас этот пик отвечает за дифракцию уже нет.
So this was the excessive fluorination destroys the graphite-like structure of nanotubes. Yeah.
Inner layers or outer layers?
So mostly outer layers, but inner layers also going to be distorted. Yes. Okay, so this is the interesting thing, because we want to make the CFX battery, right? So we assemble the electrochemical cell. So usually we have electrolyte, so then we have lithium metal, and you have CFX battery, and we look at the energy density, like milliampere hours per gram. So they have a voltage about 3 volts. So this is multi-volt nanotubes before fluorination. It has very small capacity, less than 100 milliampere hour per gram. If I fluorinate for 2 hours, so second curve, it increases close to 200. So after more and more fluorination, after 12 hours, you get more than 800 milliampere hour per gram. This is probably the highest CFX performance I have seen. Yes. So this is very large number for CFX battery. So, like I said, if you want to use it for like pacemaker, typically they use about 10 microamperes. So, because for the artificial pacemakers, they don't require very large current. If you have 100 milliampere hour per gram, you have so 800 milliampere hour per gram. So if I use current as only 10 micrometer, so then this many milliamperes, right? So if you calculate your time, so somebody can calculate this one, this will last for more than 10 years, because it only, because this is 800 milliampere hour, but since it only consumes microamperes, so this battery can last more than 10 years. That's what you need for the CFX batteries. So this is probably the highest I have seen for any carbon material.
Обратимся к графикам емкости наших батареек. Если мы сделаем батарейку из лития и нашего фторирования. Здесь у нас чистые нанотрубки, здесь после обработки, как мы видим, емкость нашей батареи заметно увеличилась. То есть, если она была около 100, то теперь она около 800. И Гамини говорит, что это самый высокий показатель, который мы когда-либо видели. Да, водород содержащий. Если мы посчитаем, какое время будет жить наша батарея, то возьмем, к примеру, искусственный кардиосимулятор. Они используют 10 миллиампер, потому что, для мышц используют. Если мы посчитаем, сколько времени продержится наша батарея, то это будет больше 10 лет. Это то, что нам нужно для кардиостимулятора.
So somebody can calculate what is the T should be, right? You can do as a homework problem. So the T will be about 10 years. That's pretty good number. So I think because of the parameters we learned from the graphene fluorination, I could do this experiment because I knew how much to fluorinate. So yeah, this pretty much what I want to talk about. So we can take any questions. But still problem is multiple nanotubes are a little expensive. That's why. Yeah, so but now we have different ways of making more better other carbon materials like graphene, so that might be cheaper.
What about the structure of this kind of nanotubes in your electrode? It's just a rest.
No, so this is the same way. You mix with some binder. So so it's standard way. Yeah. So yes, yeah. So you use what is called NDT and some carbon black. So also some PVDF. So standard polymer binders. What's that? Okay. So actually, right now what we are doing is, because this is mostly graphene, we are going to attach these functional groups, right? So basically, if you have hydrogen, we are going to fluorine, we are going to attach here. So that's simple functionalization. Now what we are going to do is replace some of this carbon with nitrogen or boron. Yeah. So how do we do that? That's a little difficult. Yes. So yeah. So what we do is first we need to break this bond. So break the bond and then introduce suppose if I have all carbon, we are going to break this bond. So at the same time we introduce, say, nitrogen into this one. So then it can Yeah, so we already did that one. So what we do is we use pulse laser. So, yeah, no, it's the same YAG laser. So we have focused the laser. So then we can break this bond because we know what the binding energy. They are typically electron volts. So the laser power actually does more than this electron volt. That means that laser can break the bond.
But you use a CO2 laser.
No. So the YAG laser.
What laser?
YAG. The what we have, the 1064 pulse laser. These are pulses, nanosecond pulses. So that's what wrong is doing. So then when we break it, we introduce the gas species, so from plasma.
But you break it on the big surface.
Yes, yeah.
Because laser beam is very...
No, we are scanning it. So typically sample is like that. So then you laser. Then we are moving the laser back and forth.
I understand.
So then at the same time we introduce, actually we use. So yeah, initially Rom was trying with nitrogen, so it didn't give good results. Now we are introducing ammonia. Ammonia has a stronger nitrogen.
But what about magnetic properties? I know it's not a topic.
Yeah, so that will be interesting actually. So once we introduce boron and carbon, that will be interesting to look at the magnetic properties.
Вот чем они занимаются сейчас? То есть обработка плазмы водородной и фторирование они уже делали. Сейчас они пытаются что сделать? Заместить один из атомов углерода в структуре гексагональной атомом азота или бора. Как они это делают? У них есть лазер, которым они проходят по поверхности. Так как энергия взаимодействия достаточно низкая, порядка электронвольт, связь разрывается, туда сразу вставляется атом азота, и таким образом получают такую структуру. Они уже сделали это, то есть они уже делали вставки из азота, и очень интересно будет посмотреть, какие же магнитные свойства будут у этого вещества.
Yeah, we can do the same thing with the boron nitride. So we can introduce carbon that way, right? So if I have boron nitride, so I can break this bond and introduce some carbon. So because BCM structure is very interesting. So we can do both this, go from carbon and introduce boron and nitrogen, or go from boron nitride and introduce carbon. That's the whole idea. Naturally, yeah, initially we like to do for graphene. Yeah. Okay, so any other questions? I think the first part was a little too detailed, that's why.